Good evening. Happy to be here. I got three things to talk to you about regarding climate change tonight, and they all start with the letter S, so it makes it kind of easy to remember. Simple, serious, and solvable. Simple is kind of how it works. Serious is why it's bad. Solvable is what are you going to do about it. You might think it's kind of weird that somebody like me who spent the last, 30 years of my life studying this would say that it's simple. You know, if it's so simple, how come we're not done with it yet? But surprisingly, the science part of climate change is remarkably simple. It's not rocket science. It's not stuff you learn in grad school. It's really stuff that you learned in the 5th grade. And my job tonight is really just to sort of remind you what you already know about that work, about that science. So let me start by asking you, you ever wonder why day is warmer than night? You ever wonder why summer is warmer than winter? Or why Phoenix is warmer than Fargo? If you think about it for a minute, you realize that in all three cases it's the same answer. The reason why day is warmer than night, summer is warmer than winter, Phoenix is warmer than Fargo, is because when you put more heat into something than you take out, it warms up. So really it's like a heat budget, just like, you know, you got a budget for your household, you got heat coming in and heat going out, and if more heat comes in than goes out, it warms up, and if more heat goes out than comes in, it cools off. Now, day to day, the heat, most of the heat changes that we have come in and out the sides. It was a nice day here today. I enjoyed myself. I live in Colorado. It was 75 today in Denver. It won't be 75 in Denver a week from now or whatever. When the weather changes from day to day, that's because the air that was here today blows away, goes somewhere else, and it's replaced by air from someplace else. And we call that the weather, right? That's fronts, that's the wind blowing from a different direction, whatever. But when you think about the climate of the Earth, guess what? There are no sides to the Earth. The Earth is round, and you can move the heat around all you want on the round ball. It doesn't change the total amount of heat. The only way to change the amount of heat for the Earth is through the top. We're not used to thinking of the Earth as having a top, but it does. And by this I mean the top of the atmosphere. So all of the heat that comes in to the Earth has to come in through the top of the atmosphere. And if that was the whole story, that would just be heat in, right? Heat in minus heat out equals change of heat. So heat in, heat in, heat in. If the sun was the whole story, the Earth would just get hotter and hotter and hotter forever, like without bound, until it melted and boiled and vaporized and something terrible would happen. So that can't be the whole story. And it's not the whole story, because the heat has to get back out. But to get it back out, the heat has to radiate out to space. Okay, reminding you of something you learned, I'm sure in grade school, they taught you there's three ways to move heat around. There's conduction, convection, and radiation. Does this ring a bell? And so conduction is like if you're foolish enough to stick a nail in a candle and wait too long, that's conducted heat coming along the nail, and it takes a material to conduct heat. But the Earth is floating in a vacuum, so there's no conduction to a vacuum. You can't conduct heat out into space. Convection is where the hot air rises and carries the heat away with it. But, you know, guess what? The air doesn't rise all the way to space, thank goodness, right? That's because of gravity. Gravity holds the air down here where we can breathe. So you can't convect heat to space, you can't conduct heat to space, you got to radiate heat to space. Radiation is, the light is radiation, the sunshine is radiation. You can't miss the solar radiation, right, during the day. I can feel it beating down on my bald forehead, and that heat is added to the world and we warm up. But the heat that goes out is heat you can't see. It's infrared heat. You can't see it with your eyes because the photons are too wimpy to tickle the little retina at the back of your eye, but doesn't mean it's not there. And if anybody's ever turned on an electric stove, before you see the red glow, you can start to feel the heat radiating off of that burner. That's heat radiation, thermal radiation, infrared heat. And the Earth is constantly streaming this stuff off into space at almost exactly the same rate that it's receiving heat from the sun. And heat in and heat out are pretty much balanced over time. But for the heat to get out, it's got to pass through the air. And the air, it turns out, is pretty much transparent in the visible part of the spectrum, which is maybe partly why we call it the visible part of the spectrum, right? We wouldn't be able to see where we were going if the air was opaque, invisible light. So we know we can see through the air. But oddly, the air is almost completely opaque in the part of the infrared part of the spectrum that the Earth is radiating this heat back out to space. And that's a weird thing, right? The air is transparent and invisible, but it's almost completely opaque in the infrared. And the reason has to do with molecules. And all right, maybe you didn't learn quite this part of it in 5th grade, but we'll get there. So air is made of molecules, everything's made of molecules. 99% of the air molecules are just these two kinds of molecules. That top one's called O2, or oxygen, and the bottom one's called N2, which is nitrogen. And both of these molecules are made of two atoms of the same element that are sort of glommed together with these shared electrons. Those little black lines are supposed to be shared electrons zipping back and forth between the two atoms of the same element. We call them diatomic molecules. Everybody knows about oxygen. If you hold your breath for a minute, you'll figure it out. Nitrogen is basically just fill gas. It goes in, goes back out, doesn't do anything because it's got these bonds that prevent it from reacting in your lungs with other things. So electromagnetic radiation is a wave of electric and magnetic fields that's carrying the energy away from the Earth, passing through these molecules of gas. And so maybe in high school you learned that magnetic fields can actually grab a hold of electric charges, these electrons zinging back and forth there. And the magnetic field is oscillating back and forth, so it actually makes the molecule get longer and shorter along that bond. And you can think of it as a vibration. The molecule actually goes woo, 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 woo. That doesn't really make that sound. I make that part up. But the vibration of that molecule has now trapped some of the energy that was propagating out to space as infrared radiation, and now it's vibrational energy in the molecule. And we call that an excited molecule because we're anthropomorphizing molecules now. But the vibrational excited molecule can then de-excite by sending a photon out of the same energy level that it took in, and the molecule will go from this excited state down to its ground state, back to this unexcited state. And that photon, if it goes up, is going to carry that energy out towards space. If it comes down, it's going to carry energy down towards the surface. But because 99% of the molecules in the air are just these two kinds, and they're both identical on either end, right? This is the only dance they know. This is the only way they can wiggle. This is the only way you can rearrange the geometry of a molecule that's just got two, identical atoms on either end. A tiny number of molecules in the Earth's atmosphere, way less than 1%, are these two other gases. The top one is called CO2, or carbon dioxide. The bottom one's called H2O, or water vapor. And these molecules have 3 atoms instead of 2 atoms. So almost none of the atmosphere is made of this stuff, less than 1%, but the parts that have 3 atoms instead of 2 actually makes a big difference. And the reason why is because they can do more wiggles, all right? So we only got the 2 hands, so we use my head for carbon, oxygen, oxygen. So now I'm a CO2 molecule. Along comes one of these infrared rays, can absorb the ray, goes woo, 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 just like the O2 and N2 did, excited CO2 molecule, and then whoa, 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 back to its ground state. But there's more. Because unlike O2 or N2, it can go each one of these different ways of wiggling this molecule absorbs a slightly different energy level of infrared photon, a slightly different wavelength of infrared light. We say that CO2 has a rich absorption spectrum in the infrared part of the spectrum. It's just a bunch of fancy scientific words. It just means that there's more ways you can rearrange the geometry of a molecule that's got 3 atoms instead of 2 atoms. Water vapor is even better because it's got that bend in it. You can get this thing going on, and this thing, and this thing, and even handsprings. We're not going to try that here. But you can see how just the basic geometry here allows for more ways to interact with the electromagnetic field. That's really all there is to it. The CO2 is a greenhouse gas, not because of greed or capitalism or Al Gore. It's just bad luck that the stuff that comes out when we set carbon on fire has 3 atoms instead of 2, and there's more ways you can rearrange a 3-atom molecule than a 2-atom molecule. So this is the nut. This is why CO2 interacts with the climate system. This is why there's a greenhouse effect from CO2. You've all probably seen the cartoon before. The sun beats down. That warms up the world. Some of it reflects back off. The part that doesn't reflect off is heat in minus heat out, and that warms up the world. All that heat's got to get out. The red arrows are supposed to be that infrared heat that's going out. Some of it gets out. That little skinny arrow goes all the way out. It's about 6% of the incoming radiation is able to be directly sent out to space by missing the CO2 molecules and water vapor molecules. But about 96% or 94% of it gets stuck, interacts with either a cloud or with one of these bee-boo molecules up in the sky that absorb the energy, and then it gets re-radiated back down to the ground. So it's actually, I have a thing in my office, which I didn't think to bring, that measures infrared radiation. So you can call it an infrared measuring device. And if I pointed it out at you, we'd see this cool movies of people in the infrared with your faces all hot and sending out infrared radiation, and your coats and hats not so much. If I take that device outdoors at night and point it up at the sky, it does not measure zero radiation coming down. It's dark outside, right? There's no sunshine at night. But if I measure the infrared radiation coming down from the sky at night, it's about 300 watts of heat coming down out of the warm sky for every square meter of the ground. So it's not zero. This is actually pretty important. If you added up all of the heat measures from all over the world coming down from the warm sky, it's twice as much heat as we get directly from the sun. That's an amazing fact, but it's true. It's a measurement, right? If I measure during the day, most of the heat's coming from the sun. There's also heat coming from the warm sky. If I measure at night, there is no sun, but there's still the sky, and we get all this heat down from the sky. If it wasn't for that heat coming down from the sky 24/7, the Earth would be a frozen ball of ice floating around the sun. Life would never have developed here, would not be a habitable planet. They'd be looking for exoplanets and they'd pass us by because we'd just be a block of ice. So thank God for the greenhouse effect. They're shining all this extra infrared heat down on us, keeping us toasty warm. So this is the common sense explanation of the greenhouse effect. Let me start with this. Many of you are old enough to remember these things. This is an incandescent light bulb. 4-watt light bulb. You guys remember these? Back when I was a boy, they were Christmas tree lights. And when my kids were little, they were the night lights that you used to find a bathroom in the hallway. And that's 4 watts. And I don't know, we don't have easy reference point here, but I don't know, maybe 2 of these chairs is a square meter. A square meter is about yay big. And if you double the number of these bee-boo molecules up in the sky, you add that much heat, 4 watts, to every square meter. So look at 2 chairs and imagine a little 4-watt light bulb there, and 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 there. Oh my God, that's a lot of 4-watt light bulbs. But it's not just this room, and it's not just Wisconsin. It's the whole planet covered with little 4-watt light bulbs every 3 feet. And that's how much extra heat you get from the sky if you double the number of these CO2 molecules in the sky. And it's not like just this evening either. It's all the time, 24 hours a day, 7 days a week, forever. Every square meter of the world getting 4 extra watts of heat. Now, if you did that and you left it on like that, it would make the world a little bit warmer. And maybe it wouldn't be a lot warmer because they're just 4-watt light bulbs, but there's a boatload of 4-watt light bulbs. And that's basically the nut. That's the story of climate change. That's how climate change works. Believe it or not, all of that was known before light bulbs were invented. The discovery of everything I just told you started with this guy, John Tyndall, in New York City in 1863. When Abraham Lincoln was president, this guy put CO2 in glass flasks and measured how much infrared heat was absorbed by the CO2 gas, and in all different wavelengths, and he published a paper 150 years ago saying that, oh my gosh, if we burn all this coal and put all this extra CO2 in the air, it's going to warm up the climate. So it's not like we just discovered this recently since it started getting warm and figure, oh, I wonder why it's getting warm. Man, maybe it's CO2. No. It's a measurement from a laboratory. Since 150 years ago, that measurement has been made by thousands of laboratories all over the world. they all get the same answer. We don't just do it in labs, we do it outside, we do it from towers, we do it from airplanes, we do it from balloons, we do it from the space station, for goodness sakes. Everybody who makes this measurement gets precisely the same answers. There's really no wiggle room about this story. CO2 really does absorb heat, and heat really does warm things up. So, common myth number one, really, the most commonly held misconception about this of all is that the reason those scientists are so sure that CO2 will warm up the climate is because it's been getting warmer lately. And for sure, it has been getting warmer lately, right? Everybody's seeing graphs like this, where back in the day it used to be colder, and then it started getting warmer, and then it started getting warmer faster. All that is true, but that's not how we figured this out. We totally did not look at these graphs and then say, oh, it must be CO2. No. We know that adding CO2, that's supposed to do something. Adding CO2 will warm up the climate because we know that when you add heat to things, they change their temperature. Okay, like when you put a pot of water on the stove and you put heat into the bottom of the pot of water, it warms up, right? Because heat in minus heat out equals change of heat. Change of heat is proportional to change of temperature. Formally, that's called the first law of thermodynamics. Change of temperature is proportional to change of heat. But you got to be some sort of egotistical Victorian Brit to think that something like that is called the first law of thermodynamics. I mean, for God's sakes, cave people knew about that, right? They put the mammoth on the fire and it got hot. But they didn't say first law of thermodynamics. They said, ugh, hot. So we know that adding CO2 to the atmosphere will warm the climate because we understand the law of ugh, hot.